Welcome back. This lesson will be about the refraction of light. Uh, May 21st is where you can find a version of these notes. I'll email out the problems to you in the same email that you got for this web link to watch this video. I'll strongly recommend that you actually read the textbook reference that I have online on, again, the 21st. Pretty good stuff in there, and yeah, that's what you'll find if you go to the class calendar. So as a quick little reminder, we're talking about light waves. So light waves are similar to water waves in the sense that you're going to have some crests and some troughs. So basically a lot of the similarities to wave propagation that you would have seen with water in a previous unit still applies to light. The only difference is light is an electromagnetic wave. Light does not require matter to travel through. A water wave obviously requires matter. Seismic waves require the ground, some kind of material for it to go through. Sound waves also require the air for it to transmit through. Light waves do not require anything. They're one of the few ways that will actually travel through the vast emptiness of space. The other wave that I can think of off the top of my head that will also travel through space would be gravitational waves, but that's a topic for a different day. So these electromagnetic waves are essentially two longitudinal waves traveling perpendicular to each other. So you have your electric field wave traveling at a 90-degree angle to your magnetic field wave as they propagate through space. And that's kind of what it looks like. I don't know how well this looks to you, but basically they're just overlap each other in three-dimensional space. So we're going to talk about refraction in this video. As a quick little reminder, I've got two little shockwave links here. As light travels from one medium to another, so I showed you this video with water waves. We talked about going from deep water to shallow water. The same rules apply. When light's traveling in air or even in a vacuum, it's pretty free to do whatever it wants. Once it gets into a transparent material, so in this case glass, glass would be optically denser than air. So when I use the word density from this point on, I'm usually talking about its optical properties, not its actual density with respect to mass and volume. So glass in this case, there's many different types of glass. This is just generic, not really supposed to pay too much attention to the type in this case. When the light waves pass into this glass, the waves slow down because it's harder for light to travel through this transparent material. So because of that, the wavelength shortens up, the speed shortens up, frequency does not change because the frequency never changes once a wave is created. So because we're traveling with this, well, this would be a water wave. Light waves, we tend to use beams, straight lines, but you saw this video, this little shockwave flash in a previous video lesson. So it alters the speed as well as the wavelength properties. And if you hit at an angle that is not traveling straight in with the normal line, so if you're traveling at an angle to the boundary, so in this case you have two different mediums, you have air and glass. So if you hit at a different angle, when you get into this denser medium, it will slow down, but it'll also change direction. This change in direction is your refraction. So this is what it would look like if it was a light ray. You'd have that beam of light. It would hit this boundary right here. You'd have a normal line on both sides of the boundary. The normal line is always going to be perpendicular to that boundary between the two mediums, right? And the normal line doesn't technically exist, so of course it's always a dotted line. And then you'd have to play around with your angle of incidence and angle of refraction. Now in the waves unit, you weren't given numerical values other than, hey, if this is 50 degrees, what should this be? And then your answer would probably be less than 50, and that'd be good enough. We're actually going to calculate these values now in this video and the next video. So that's what we're going to do right away. So we have a refraction. The light ray bends towards the normal, which is a good indication that it is slowing down in this denser medium. So that's basically what refraction, and it leads to neat things like this. It looks like this man's head is decapitated. Well, it looks like he's holding his own head because light is traveling faster in air than it does in water. You would probably notice this if you had a glass of water with a straw through it or in it, and you look at it, line your eyes up with the surface of the water, you'd see that the straw will basically do the same thing. It looks like it's broken. So that's just because light travels faster than air than it does in water. And down below, You have light traveling in water, which is fairly transparent, as well as glass. So it has to travel from water to the glass, then to air. So you're going to get refraction a few times, and it does all sorts of neat little effects like this, where as it looks like this man is holding his head, all because of that. So what's actually happening between the two boundaries? Again, just like regular wave properties, when one wave travels into a new medium, you are going to get partial reflection. We're going to ignore this. I'll leave it on the diagram, but you can more or less ignore the fact that yes, it's going to still reflect. Some of it will reflect, some of it will transmit through. So that is your partial reflection, and this is your partial refraction. On here, I have the original path. So it's just a very lightly dotted line, just so you can kind of see how far it's strayed from its original path. In this new medium, so water is a lot denser than air, so light is going to slow down quite drastically. When it gets into this new medium, it's not going to travel at 3 times 10 to the 8 meters per second. So when it goes into a denser medium, it's going to slow down and bend towards the normal line. When it gets into a, oops, wrong way. When it gets into a less dense medium, so suppose we go the opposite direction, when you go from water into air, your refraction is going to increase. So the ray of light is going to bend away from the normal line. So whereas before it was hugging closer to the normal line because it slowed down that new medium, now when you go from medium 1 into medium 2, from water into air, the light ray would bend away from the normal and it would get closer to that boundary line right there. It's not going to affect how it reflects. Whatever your angle of incidence is should still be the same as your angle of reflection, so that the law of reflection is never going to change, but most of the time we just ignore the reflected ray when we're trying to diagram these. So when you go from a dense material to a less dense material, it's the refracted ray is going to bend away from the normal line. Oops, I'll just delete that. That was a copy paste error. It's going to bend away from the normal line and speed up. So it's going to speed up in this new medium. So mathematically, that's where we get introduced to the index of refraction. And if we're going from the case of our medium 1 being a vacuum, so the vacuum of space, or just absolutely no matter whatsoever, that's what a vacuum is, into our new medium, we can call that the absolute index of refraction. And that's where we get our index of refraction values for n. All it is a ratio between how fast does light travel in a vacuum, so that's the absolute speed, of our universe. Nothing can travel faster than light in a vacuum, divided by how fast it's traveling in said medium. So if I want to know how fast, if I want to know the index of refraction for water, I just have to take my speed of light and divide it by my speed in water. So that gives us a table of values of all sorts of index refractions. You don't have to actually calculate the speed of light. Typically, all you just need to know is what the medium is and what its absolute index of refraction value is, and then you can just figure out how fast light is traveling in each of these things. Now you'll notice for a lot of these things like plexiglass, lucite, crown glass, a lot of their index refractions are fairly similar, right? There's not much difference between ruby versus lucite. They're all fairly similar, and depending on which chart you look up, will give you slightly different values. So this chart, with the exception of the first two, this chart is given to you with just 3 significant figures. When it comes to the difference between air and a vacuum, you need 5 significant figures because there's not a lot of difference between light traveling through air versus light traveling in a vacuum. So most of the time we just kind of ignore this difference and say it's about the same. But if you're doing that high-end physics stuff where you absolutely need to know the difference between them, then you'll probably have to actually get in more significant figures. So for instance, if I actually compare glass, crystal glass with ruby, three significant figures wise, it says they're the same. If I go a few extra digits further, maybe they'd start to get different. They're not exactly, they don't exactly have the same optical density. I forget what those numbers are, and they're not really important. They can be looked up if you want. So you have that chart in your notes. Use this chart when you're answering your questions. If you do your own search and find a website called the Engineer's Toolbox, you might have slightly different values because there's more than one type of plexiglass. The chart I took this from has used the type of plexiglass where it had the same index refraction values of 1.47 as glycerin. So you might have some variance if you look around somewhere else. So just use this chart. So I'll do a couple questions just as an example, and then I'll stop this video. So suppose the speed of light in a liquid is 2.25 times 10 to the 8 meters per second. What is the refractive index of the liquid, and what is the liquid? So um, again, you're going to be using these ugly values in your calculator, so please make sure you know how to enter in scientific notation into your calculator. You'll see one or two buttons. You'll either see a button that says double E, or you'll see a button that says EXP, or if you're using one of those high-end HP, or sorry, which one are they called? The TI Inspires. I think you have to go somewhere else to get them. Actually, no, TI Inspires have this. Maybe it's the Casios that have a different button. I don't remember. You guys have your own calculators. You figure it out. So basically what I'm getting at is if you press either of these buttons, so for instance, if I want to use scientific notation, I would just hit 2.25 in my calculator, and then I'd press one of these two buttons, and that will automatically do this for me, right? You may not see it say times 10 in your calculator. It'll just automatically assume whatever number I hit in next. So in this case, I just punch in 8 next to my calculator, and the calculator will recognize it as what you see here on the screen. So that's one way to get around that. Don't hit times 10, then press this button, because then you're going to have 2.25 times 10 to the 9. So don't do both. Just use one of these two buttons. It'll make your life so much easier. Okay, so moving forward, when you're doing these calculations, again, always state the equation. Since you weren't given going from one medium or the other, we're just going to assume that we're using our absolute index refraction equation. So we're comparing to the speed of light in a vacuum. So that's just a matter of doing the ratio. 3 times 10 to the 8 meters per second divided by 2.25 times 10 to the 8 meters per second. You'll see that since you have 10 to the 8 in the top and 10 to the 8 in the bottom, you can just actually cross all those out. The units cross out as well, because as you notice, there's no units for any of these index of refraction values. And then you can just punch in your calculator. It'll probably give you that. Please don't ever write that number down. Stick with what we have here. We have 3 sig figs for the most part. I gave you a number of 3 significant figures, so your answer is probably going to be just 3 significant figures, and that's good enough to go look at the chart and say, oh, it's probably water. If I ended up getting 1.34 or 1.32, if the question was slightly more complicated, I'd probably just say, it's probably just water anyways. So do keep that in mind. If you had to use this number later on, I would have kept a few more 3s afterwards, but we're done with this question, and that's good enough. So if you, for instance, wanted to figure out the speed of light in lucite, so lucite, if you don't know what that is, it's just a type of plastic. It's a hard plastic. This is a quick little Google search. Like one of the first 2 things I found were just a guitar made of lucite and some, I guess, poor version of Cinderella not having glass slippers. She has lucite slippers. That's a bad joke. Okay, moving on. So if we're trying to figure out the speed of light in lucite, it would just be a matter of finding your little table, look for the index refraction value. Oh, lucite is 1.51. And great, so you write that down, and then you just perform the calculation. Take your equation for the absolute index refraction value, do some quick manipulations. So in other words, I want to do the game of switcheroo where, because I'm looking for my speed, I essentially just want to trade places with my absolute index of refraction value. So in other words, you just multiply by V over N on both sides of the equation in order to get V all by itself. And it will look like that. Just a matter of plugging in your numbers at this point. 3 times 10 to the 8 meters per second divided by 1.51, and we'll give you something like 2-ish times 10 to the 8 meters per second. I'm going to keep it as 1.99 because obviously 3 significant figures were given in the question, or at the very least you got 3 sig figs from this chart. So just do represent your answer as 3 significant figures. Just be warned, if you're doing these calculations and you're trying to calculate the speed of light in any substance, you cannot calculate a number greater than 3 times 10 to the 8, right? If you ever get something greater than 3 times 10 to the 8, you did something wrong. Nothing in our known existence and universe is faster than the speed of light in a vacuum. We can accelerate electrons and particles faster than the speed of light, but they have to be traveling through like water or another medium, because then we can kind of figure that out. But when it comes to the speed, the speed limit in a vacuum, absolutely nothing is faster than light. So do keep that in mind whenever you're calculating your work. Nothing should be bigger than 3 times 10 to the 8. All right, I've said my piece. Moving on. So sometimes we go from one medium to another medium to another medium to another medium to another medium, just like the picture of the man holding his own head in the little pool there. All right, light would have to travel from water into some kind of glass, then into air. So there's 3 mediums. Here we have, just as a random thing that I stole from the internet, here I have 1, 2, 3, 4, 5, 6 different mediums. Well, 5 technically, because I start and end with air. And when I travel from one medium to another medium to another medium, light is going to refract depending on what you're going to and from. So in the case of going from air into flint glass is more dense. I can tell because of its absolute index of refraction. It's a much larger value than air. It's going to slow down. So this is a little bit hard to see on the video. It's going to get closer to the normal line. It's going to refract and slow down a little bit more. And when you go from flint glass into water, water has a smaller index refraction value, so it actually starts to bend away from the normal line. So if you kind of notice, the angle here is a little bit um, a little bit smaller than the angle here, but not by much, because it's not a great difference. It's only 0.3 as far as uh, or 0.3 as far as our index refraction value is concerned. Versus diamond, diamond is one of the largest index refraction values, so it really slows down when it gets into diamond. So therefore, our refracted angle between water and diamond is really, really small compared to my incident angle, and so on and so forth. In fact, in the end, by the time I get to the end here, I go back into air, and you'll notice the large difference between cubic zirconia versus air. You will see a difference between the incident angle and the refracted angle. Air is a lot less dense than the cubic zirconium, so therefore it's going to really bend away. And if I extend my initial ray, all right, that's why it's dotted, it's just extended, you'll see that it does come out. Since it comes out into the same medium that started in, and all of these mediums are parallel with each other, the emergent ray is also going to be parallel with the, so this is the emergent ray, it'll also be parallel with the original path. All right, so it has a little bit of what is known as lateral displacement. All right, so it's pushed off to the side a little bit, all because it went through all these different mediums. So what I have here in text is just what I said out loud. I forgot I typed it all out. So between each of these boundaries, it's going to slow down, refract towards normal line. Between this boundary and that boundary, it's going to speed up and refract away from the normal line. So basically, depending on whether I'm going from a dense medium to a less dense medium, or a less dense medium to a denser medium, is going to determine what happens with light. So these are kind of things I sort of expect you guys to point out after you do most of your questions. What does light do when it enters into the new medium? It's just a simple matter of stating something like this. Light's going to slow down, refract towards normal line, or it's going to speed up, refract away from the normal line. So that brings us to the relative index refraction, because you're not always going to go from a vacuum into this new medium. We might be going from 2 different mediums that aren't a vacuum. So when that happens, we rely on the relative index refraction, and that usually tells physicists what's actually happening to the light. So very often we don't actually know what either of the speeds are. Like, not many people can just, unless they're working with it a lot, most people will just not know what it is. Like, oh, how fast does light travel in zirconium or zircon? I was like, oh, I don't know. It's something I can calculate. I just don't know what it is off the top of my head. So what physicists tend to do is use something known as the relative index of refraction. That's when you're comparing light traveling from one medium to another, where neither of those mediums are a vacuum. So because we don't typically know what V1 or V2 is, we will combine that with our absolute index refraction equation. So we can manipulate the absolute index refraction equation to solve for V1. We can manipulate the absolute index refraction to solve for V2, and then we can actually put them in, and we have this horrible cluster of an ugly fraction. So we have one fraction divided by another fraction, just by substituting in for V1 and V2. And with that, we hopefully remember how to divide by fractions. So I'm going to just set them side by side, right? Just instead of a fraction like this, I'm just going to set them side by side. And hopefully you were told that when you divide by a fraction, you have to flip the second one into a multiplication. And when you do that, you'll see that your speed of light will actually cancel out altogether, and you're left with the actual equation for your relative index of refraction. N2 divided by N1, the index refraction of medium 2 divided by the index refraction of medium 1. And that'll give you the same result as if you took velocity 1 divided by velocity 2. So they're actually, if you go back to this, they're actually the inverse of what you see as far as their velocities are concerned, medium 1 to medium 2. But if you're just comparing the indices of absolute index of refractions with each other, you go medium 2 divided by medium 1. So essentially, you have this little nonsense here, 1 and 2. This is just referring to going from medium 1 into medium 2. That's important only when you have, I still expect you to write that out, but it's important because you might not always go from just one medium to the other medium. You might have an ugly case like this where, okay, I'm talking about going from medium 3 into medium 4. What is the relative index of refraction? Well, that's when you refer to it as 3 and 4. Right, so these aren't exponents, these are subscripts, and it's just giving you an indication of which mediums are we going to and from. Okay, and that's the whole purpose of those numbers there. So it does give you an idea of what numbers to put where. The second number is the one that you put in the top of the numerator. The first number is what you put in the bottom in the denominator. So this ratio has meaning to physicists. So what you get in the end, since it is a ratio, you're just going to get either a number that's greater than 1, a number that's equal to 1, a number that is less than 1. So each of these three scenarios tell the physicist something. If your relative index of refraction gives you a result that's greater than 1, well, that tells you that you're going from a fast medium to a slow medium, if you will. So light's going to bend towards the normal line. So that's kind of the example that I have here. It's going from a fast medium into a slow medium, and then therefore the refracted ray is going to bend towards the normal line. This is an indication that it's slowing down. Okay, if you have two that are optically similar, you're going to get a result that's 1, and when that happens, no bending occurs. There's absolutely zero speed change, and I'll show you what that means in a minute. And if you get a value of your relative index of refraction that is less than 1, that means light's going to bend away from the normal and therefore speed up. So it's the opposite effect. It's going to hug near this boundary line. It's going to bend towards that boundary line a lot more. This is what I mean by when there's no bending. So I usually do this in class. Pyrex is a type of glass. It has a very similar index of refraction as cooking oil, so canola oil. So here I have, well, it's not me, somebody else put this online. Here's two things made of Pyrex. So here's a little stir rod that you would have seen in chemistry class. And you'll notice if you follow that stir rod into the cooking oil, the canola oil, it disappears. You cannot see it. Likewise, you can see this test tube in here until they fill it full of canola oil. Then it looks like it just completely disappears. It becomes invisible. And that's because the reason why you can't see the glass rod versus you can see this test tube for just a brief moment in time is because there's air inside this test tube. And so therefore light is going to refract differently in the air portion of this open test tube. So when they fill it up with canola oil, it's going to therefore have the exact same index of refraction as the Pyrex. And so therefore once light bends into the original beaker, there's going to be no more bending of light until it exits the entire medium, and therefore making this seem invisible to the eye. And that is what needs to be done if you ever want to build a Harry Potter cloak of invisibility. You have to try to somehow find out how you can make your index of refraction the same as the air around you. And once you can determine that, don't ask how to do that. I have no idea. There's lots of other people trying to figure it out. But once you can figure out how to match index of refractions of air, you can more or less make it look like you are invisible because there'll be actually no refraction of light. Anyways, I'll stop talking about that. Let's just move on. So light ray passes from crystal glass into water. What is the relative index of refraction? So I have this drawn out, and very often I like to draw these out. So you have the normal line. I just drew that down too far. I like to draw these out just to kind of get an idea of what's going on. So typically I'll look up my two values. So crystal glass and water, I'm going from crystal glass. So that's going to be medium 1. I'm going into water. So that's going to be medium 2. I drew them top and bottom from each other. If you look it up on your chart, so you have, again, quite a few different types of glass, crystal glass, 1.54, and water, 1.33. I know I'm going from a slow medium into a fast medium because these are ordered from light traveling fast to light traveling slow. Water is higher up on the chart. It has a smaller index refraction value, so I already know what's going to happen as it goes from one medium into the other. If I'm traveling in this crystal glass and I move into water, my refracted angle should bend away. That's my angle of incidence. This should be my refracted angle. My refracted angle should be visibly larger, okay? So that's kind of what's happening physically. Mathematically, to calculate my relative index of refraction, I'll just bring out the equation and then do the division. 1.33 divided by 1.54, just do a little bit of math, 0.8636. I'd probably only have that as three significant figures, 0.864. And then you just sort of state what's actually happening. The relative index of refraction is less than 1, right? Less than 1. Therefore, ... those three dots like that in the triangle means therefore light is bending away from the normal, and therefore this light ray is speeding up in the new medium. Okay. So that brings us into the angles. When you're calculating the angles, you actually are following the law of refraction. And the law of refraction says, well, the first law of refraction says the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant. So regardless of what this incident angle is and a refracted angle is, if you're going from, say, crown glass into water, these two angles will change in such a way that when you divide them, right, if I start off the angle of incidence of 5 degrees and 10 degrees and 30 degrees and 40 degrees, et cetera, et cetera, et cetera, this refracted angle will change in such a way that the ratio, if you divide them together, you'll always get the same value for your relative index of refraction. And we typically would have done a lab for this in class, and you would have seen, you would have seen that for yourself. Now, when you do it experimentally, there's some slight variations, but with this number here, and that's mainly due to measurement error. But in reality, they should refract in such a way that this value will not change. The second law just says that they're all coplanar. All right, the incident ray, the refracted ray, they're on opposite sides of the normal at the point of incidence, and all three are in the same plane. They're not going to suddenly jump up into the Z direction unless something's already in the Z direction. So typically, you just have to worry about the first law. So what that means, one more example with the first law of refraction. So it says a light ray passes from one medium to another with an incident angle of 46 degrees and a refracted angle of 27 degrees. What is the relative index of refraction? So I don't know what medium 1 is. I don't know what medium 2 is. I wasn't told, and the question just says from one medium to another. So I have to use the angles to figure out what the relative index of refraction is. And I always find that the angles give away a lot more than the actual numerical values, because I can see, especially when I draw it out, I can see that if my incident angle is 46 and my refracted angle is 27, I know I'm moving into a denser material because my refracted ray has become smaller, and therefore it bends towards the normal line, and therefore this must be a denser medium. So that's just something I'd look at right away. So since I have two angles, I'll find the relative index of refraction by just doing the first, by doing the law of refraction. So sine I divided by sine R, and do make sure you're not in radians. You have to be in degrees for this. If you're in radians, I can't help you. So make sure your calculator's in the right setting. Plug in your numbers. Oh, and this comes up every once in a while, year after year. Do not just do 46 divided by 27. I forgot to say that one. Type that in when I'm doing my video. Don't just do that, right? That's not going to work for you either. You have to go sine 46 divided by sine 27, right? So usually I recommend to most students to just maybe write out those values. Don't erase your calculator. Some people just go 0.7 divided by 0.5, and it's like at that point, no, you're going to be way off. So do not simplify these numbers. Keep the whole number in your calculator, because typically those trig values are perfect ratios. I'm not going to get into the math behind that. Grade 11, you should probably have had enough lessons on trig to walk you through it. So don't erase these numbers. Typically, I'll only usually write down 3 significant figures. Every once in a while, I'll kind of write in 4 or 5 and just go dot, dot, dot to kind of remind students that maybe keep that whole value in your calculator. So if you don't believe me, take 0.7 divided by, well, this would round up to 0.5. You'll see that you get something way different than this number here. All right, so if it comes down to it, this is the correct answer. I expect you to keep these whole values in your calculator. If you get something other than 1.58, it's just wrong. All right, so do make sure you're careful about that when you're punching these numbers through your calculator. Anyways, so I got a number, my relative index for refraction is 1.58. So that tells me it is greater than 1. Because my relative index for refraction is greater than 1, therefore my light is bending towards the normal line, and therefore light is slowing down. Okay, so again, with a diagram that I kind of drew in, doesn't tell you to draw it in, but I drew it in. It's enough of an indicator that, oh yeah, that's definitely gonna have to slow down if it goes towards the normal line. Okay, I'm gonna stop there and catch my breath. Again, please make sure you read the textbook reference. It starts on page 9. It wouldn't hurt you to read the whole thing. Start right on page 1 and just go all the way down. There's lots of diagrams and pictures in there, so it's not like it's straight 9 pages of textbook reading before you get to where the stuff starts. So do give it a read and attempt those problems. As you can probably tell, they're not that hard. Okay, I'm going to record your next video. Stay tuned.